Imagine throwing a party in a normal-sized room with fixed walls, but when you open the door, an endless number of guests pours inside. Think about what actually happens to that physical space. You have an endless amount of physical matter flowing into a room that cannot grow. Since the walls won't budge, your guests can't spread out forever. Eventually, they are forced to do one of two things: stack on top of each other or crowd together infinitely tightly. In mathematics, we call that never-ending line of guests a sequence, and those inevitable pileups, we call them limit points. A limit point is the physical certainty of a traffic jam that happens whenever you trap infinity inside a boundary. Let's give our guests a strict mathematical rule. Once inside, they are only allowed to stand on exactly two specific floor tiles. This animated diagram represents our room as a number line trapped between walls. Our line of guests jumps into the room, perfectly alternating between just two spots, the number 1 and -1. We have an endless flow of people, but only two valid locations for them to go, so they form massive, infinite towers on those exact two spots. Because of that perfect repetition, both 1 and -1 are valid limit points for this sequence. Now look at this updated diagram for a different rule. Think of this as a tired sequence. Our guests are trying to walk toward a rigid wall labeled 0, but each step they take is only a fraction of the last. The first guest stands at 1, the next at a half, the next at a third, bunching closer and closer to the wall. Mathematicians call the tiny sliver of space surrounding a specific destination a neighborhood. No matter how closely you zoom in on the neighborhood right before that 0 wall, you will always find an endless, impossibly dense cluster of guests trapped in that gap. That means limit points emerge in one of two distinct ways. The numbers either perfectly repeat forever, or they endlessly crowd closer to a single uncrossable destination. But what happens if we tear down the walls of our room entirely? Imagine an open highway stretching to the horizon. This represents an endless counting sequence, 1, 2, 3, 4, and so on. Without boundaries stopping them, our line of guests can simply keep walking straight forward into the distance. Because they have infinite space to stretch out, nobody is ever forced to stack on a single tile, and nobody gets crowded against a wall. Everyone gets their own space. This shows us an absolute rule. An endless line of numbers on its own does not create a limit point. You need an infinite sequence and a boundary to force a pileup. If you can picture that bounded room in your head, you already understand a major rule in advanced calculus. This concept is formally known as the Bolzano-Weierstrass Theorem. The theorem states exactly what we just observed. Every bounded sequence, which is just a line of numbers trapped inside a room with walls, absolutely must have at least one limit point. We can add one final variation. Take a look at this diagram showing a number line trapped between two walls. We call this a monotonic sequence. Our guests walk in a single direction, strictly forward. They never bounce back and forth. Since these guests can never turn around to revisit an old spot, they can't form a second pileup behind them. And because the wall blocks their path, they eventually run out of room to spread out. This lack of backtracking forces the sequence to stabilize in one specific location. That's why a bounded monotonic sequence will always have exactly one unique limit point. The concept of infinity can often feel overwhelming and intimidating, but when you put it inside a rigid boundary, it follows strict, predictable rules. By tracking these pileups, we can see exactly where an endless sequence will eventually settle.